normalized. So you take that one. That's kind of, given its standard deviation, I should expect something like that. I'm not gonna do it for deciles, but you could. Kind of argument that I'm gonna make is, let's get a estimate of mean and standard deviation. Smaller. If I also collapse the ribbon, I get more real estate here. Now let's think about the non-normalities. First, to kind of get an idea about the shape of the distribution, select the data, hit insert under okay, histogram. Let's move this to a new sheet. Excel's histogram algorithm is not that good, but let's see. If you roughly look at this chart, would you consider this a symmetrical distribution? Yes or no? Symmetrical means you kind of took, went to the middle, the mode here. The left of the graph is pretty much a mirror image of the right of the graph. Do you think this one is symmetrical? It's going to be very rare that it will be, but it doesn't look so. If anything, which tail seems to be longer? The left tail or right tail? Left tail. So this distribution is left skewed, which is kind of very common in stock returns. Since this is a S&P 500 index, the skew is actually not that pronounced. Had we done this for individual stocks, it would have been a lot more pronounced. And we're going to also ask ourselves the question whether or not the tails are fat. It's not that easy to figure that out from a histogram, but we can figure it out ourselves. For example, 5 percentile, for the normal distribution. I'm going to figure out what would be the fifth percentile for a normal distribution that has this mean and this standard deviation. That means we need to invert the normal distribution. The function for that is norm inv. I think it's norm dot inv. It has 3 arguments. What's the probability? 0.05. So I want 5% probability to the left of the point I'm going to find. I want the mean to be that and standard deviation to be that. This basically says if stock returns were normally distributed, the fifth percentile would have been at negative 3.75. Make that a little bit different color. The actual, we already have it here, 360. Let's do the first percentile. Norm.inv. .01. That's the mean. That's the standard deviation. And the actual first percentile is, let's copy the format. Now let's think about that. One percent of the time in actual data, you're going to lose 6.66% of your investments in 1 week. But had the distribution been normal with the same mean and standard deviation, that number would have been 539. Now, why is this important? A, this shows that the left tail of the distribution, actual distribution, is actually fatter than normal distribution. Whenever the actual extreme percentiles are higher in absolute value compared to what would have been implied by a normal distribution, those tails are fatter. The idea of fatter is we can actually figure something out. What percent of the distribution, actual return distribution, has returns less than 539? So let's find out. Percentage of data points with less than we can do it in a lot of ways, but easiest way would be there's a function called COUNTIF. Okay, I'm going to count the number of data points that satisfies a certain criteria. The first range is for the criteria. Select all of them. And the criteria is going to be less than negative 0.0539. turns out a total of 31 data points out of all of these were less than negative 0.0539. If I divide that with the total count of numbers, do that right. Now let's think about what that means. Had the data been normal, 1% of the time, we should expect returns to be less than negative 539%, given that it has the same mean and standard deviation. But in the actual data, you have about 2% of the data points less than that column. That's what we mean by tails being fat.